Thanks for being here. Excited to be here at AI Dev. Today I'll be talking about a scalable distributed cache using Apache Arrow on top of Kubernetes. I'm Ricardo Aravena, and I'm open source enthusiast, and I've been working with the CNCF for many years. So I'm also in the CNCF TOC now. So yeah, happy to be here. So a little bit about what I'm going to go over today. So some of the technical challenges around ML training and understanding them. And I'll introduce this Apache Arrow data cache solution. And I'll deep dive into some of the components and what's in the cache internally. Then I'll talk about a demo, and then I'll give you a brief roadmap and on some of the upcoming features. So the ML ops pipeline, so this is what it looks like at a high level. So you have a data preparations step, and that's where you massage the data and to make it ready for the model training. Then you have some model development where, like data scientists, write code for training data or massaging data. Then you have the model training step, and that's where you actually do the training operation, and you store that into an artifact repository like a model registry. Then you do model optimization, that's like fine-tuning or changes to your model. And then finally, you have your model serving, that's your inference. To tie it all together, you have a workflow mechanism, and you also, a model registry as a common storage for all these different steps. So specifically, Kubernetes and Kubeflow. So Kubeflow is a project that allows you to run all these different steps on top of Kubernetes, and it does actually have components for each one of these areas. So for data prep, it has a Spark operator. Then for model dev, it has the Kubeflow notebooks, and for registry, it has a Kubeflow model registry, and then to train the model, it has this component that we'll be talking about specifically today, the model, the Kubeflow trainer. It does also have a model optimization component called Knative that is for auto ML, and then for serving, it uses kserve. But this is Kubeflow specifically for you can swap some of these pieces if you like to as well. For example, for serving, you can use things like VLLM, which is a very popular project now too. Now, Kubeflow also has a mechanism to tie all these different steps together. It's called Kubeflow pipelines. So the Kubeflow trainer. So this is related to our Arrow cache, and so it is a component that you install on your Kubernetes cluster, and it allows AI practitioners and platform engineers or cluster operators interface with like these train jobs. So the AI practitioners use like a Python SDK, and they can create a train job, and cluster operators can use something like kubectl to interface and create the training runtime, but they also can use kubectl to create a train job. And then on top of that, there are some Kubernetes resources that allow you to optimize for training. Those are JobSet, and the JobSet actually manages multiple jobs in different Kubernetes nodes. So this is what it looks like for a single node machine learning training workload. So you pick up all the resources from the disk or the data, and then you load that data in parallel into a RAM. And then using CPU in your machine, you can transform that data, and then you load that data into in batches for your training, and that could run on accelerators like GPUs, right? But some training can run in CPUs, but not necessarily very efficient. But that's what we'll demo today. But in real production environments, you want to use like an accelerator. And then for multi-node training, in similar fashion, you load that data in parallel, and you load that into the different nodes. And then for each one of the nodes, you load the data in batches to do the model training. So you're doing a lot of different operations here in the node, ahead of time to do your training in terms of data. Like if you have large amounts of data, so that's a challenge. And from a training perspective, you have a code snippet here. So when you do training, you train in different epochs. So the more epochs you train, you improve the output of your model. So here we have a single epoch. You pick up the data. You access the data here on the training loader, and every time you're accessing this data, then it could be inefficient, right? So hence the challenge, with loading lots of data and the reason to have a cache. So data we think of it as the new bottleneck for training. Some of these data sets will continue to grow exponentially. So GPU power will continue to grow as well, and this is outpacing the way to load data. So cloud-native environments will continue to be more complex. So we need ways of supporting heterogeneous environments, do shuffling of data across different epochs more efficiently, and sharding that data across the multiple workers. So here's our Arrow data cache solution. So with this solution, we are decoupling the data preprocessing. So this is the preprocessing is done ahead of time. It supports Kubernetes, so it runs on top of it, and it uses new mechanisms. For example, LeaderWorkerSet, LWSet, which is a pretty recent feature in Kubernetes, and it allows you to have a head node with multiple workers. And this will be a shared layer that can be accessed by multiple nodes and multiple training jobs. And it also provides zero-copy access using this Apache Arrow mechanism and using Apache Arrow flight mechanism. So yeah, so this cache sits in between storage and compute and creates that layer that accelerates training data for training, and it also improves the training speed for that reason. We do have some mechanisms that are part of how you pick up data and how we pick up data for this cache. And so we use Parquet as a data storage format, and it's a columnar compressed storage format. And it's very popular nowadays for data sets, and so it supports also large data sets, and it has a very low storage and I/O cost. Now for safe access and easy access, we use Apache Iceberg, and so these are tables that are created on top of the Parquet data files, and this is an open format. It's very popular nowadays. It does have it actually is lower in terms of access and has higher transfer costs, but it provides some other mechanisms like openness of format, and so it makes it easy for users. So that's why we actually read in Apache Iceberg tables. So as far as the implementation, going down more to the details, we have the efficient storage in Parquet format and the tables in Apache Iceberg, and then we load up that data into Apache Arrow, that actually constitutes our cache, and we store the data in memory, and that's how Apache Arrow works. And then so looking at more at the details, we have an Apache Iceberg table here. Say like you store this in Amazon S3 or blob storage, and that is actually read by our head node, and our head node actually splits the data into different rows, and then it also it splits the data into different batches. Like the batches are loaded into the number of nodes that we have. So in this case, we have 2 nodes, but we can have multiple nodes. but then the head node takes care of that. And then once that cache is actually loaded, we have the Apache Arrow flight mechanism to do zero copy when you do your training job. So here we have an example with PyTorch. PyTorch reading the data from the cache directly using zero copy. And a little bit more about how Arrow flight works and the zero copy transport. So at the top, you have something like a standard conversion with JDBC, like how you will connect to fetch the data using JDBC. And there's a conversion step there with Arrow flight. There's no conversion, so it's as zero copy, so it's more efficient and more direct. And then once we have the cache built, we can also access this cache from multiple training jobs. And so here on the left, we have we get the flight info from the different data nodes and what part of the data rows we want to access, and we do a do-get Apache flight, Arrow flight operation to get the data. And on the right, we also have another training job that could access that data by accessing the head node and knowing where to get that data from. And how we put all of this together, we use a library called Data Fusion that actually picks up the data from a Apache Iceberg table, and that data is actually stored in Parquet. And then we store that data into the different data nodes, and then finally we pick up the data, the rows that we need from a framework like PyTorch, or it could be any other framework, data training type of framework. We do offer also Kubernetes integration. So it runs on top of Kubeflow. You can use a TrainJob from the Kubeflow trainer, and it uses a JobSet mechanism from Kubernetes, also LeaderWorkerSet, LWS. But it can also run with other frameworks like Volcano and Kueue. Like if you have batch type of jobs, then you can pick up that data from the cache. It's just if you're using PyTorch with Volcano, for example, or any other machine learning training framework. In framework compatibility, I mentioned this before, so, we support PyTorch, but you can also use the cache with other frameworks like TensorFlow and JAX and any other framework that you may have for training. So now I'll actually give a brief demo of the cache. So hopefully everything works okay. So I created this kind cluster. I actually created this demo on my local laptop, but I had issues with the network connection, so I ended up actually setting up a kind cluster in a cloud server. So, because I created the demo when I was in the US, and it was actually faster, but when I got here, somehow it wasn't working, so I ended up actually working in a cloud, or setting it up in a cloud instance. But here it is. So it's a kind cluster here. I don't have any pods here, so I'm gonna go ahead and deploy my cache, my Arrow cache. So I have a script that I'm using the IMDb dataset from Hugging Face to populate the cache, and then I'm going to use this dataset to do a basic training of the Steel GPT-2. It's a very small model, it's just for demonstration. So I have the script that sets up the cache. Just give me a second. Yeah. And I'm storing my data in AWS as well, so I'm using this IAM role, and I'm using LeaderWorkerSet, the CRD, and the feature in Kubernetes that allows you to break down your head and your working nodes. So yeah, so I deploy my cache. So if I do a get pods, my cache is running. So this is running actually much faster because it's already set up. So if you see, this is the head node, LeaderWorkerSet 0, and then you can see that we successfully connected to all the workers, and then we actually populated the cache. So if you look at the logs of the workers, you'll see that worker 0 starts with cache index 0, and then worker 1 starts at cache index 5000. It's how we break down the data, basically. So, and then these are just 2 nodes, but if you have more data, that you would actually find like more or higher numbers here, or more batches of data. All right, so my cache is deployed. Now I wanna actually run a train job. So I created this. Let me test the. I don't know how much time I have, but let me test that we are connected to the cache for a second. So I have this port forwarding that is actually connecting to the workers, and I have this little script here that runs operations on the cache. So this is IMDb, and then we have a demo client here that runs operations on it. I need to source. Just a second, source. So I'm activating my virtual environment that has the dependencies for this. So here we are connecting to the cache, and we see we're retrieving like IMDb reviews, or like movie reviews, which is a data set. Okay, so that's for retrieving some of the data from the cache. But then I have this other job, which is, let me briefly kind of show what it is. So this training job, basically, it uses PyTorch simple or basic container image, and I install some dependencies here, and it basically runs my Arrow cache client application. So that is actually applied through. And then a data scientist would actually do this on a Kubeflow notebook or a Jupyter notebook. Right? But here, because I'm doing the operation directly from kubectl, I'm just applying the YAML manifest. Okay, so I created the job already, and this is a CRD in Kubernetes called TrainJob, and you can see it's already there. And this actually creates a pod with the job. So if you look at the logs of that train job, you can see that it's actually running. So if it went really fast, right? So this is where it picked up the data from the Arrow cache from each one of the workers, and then it started the training job. It started downloading like GPT, Distill GPT-2. And then, yeah, this is just running training now, and it should take just, yeah, so run 20. And this is like a very basic training, and the model was uploaded back to AWS S3, the checkpoint of the model. So essentially, we're fine-tuning here, like from Distill GPT-2, starting with the Distill GPT-2 model, and then using our IMDb data in the Arrow cache, and then training using that data, or fine-tuning using that data. So that's it for the demo. I hope that was useful, but happy to answer any questions afterwards if you have questions about this cache. And then so for the future, we're thinking about implementing more things, like more intelligent prefetching of data to reduce that latency, direct GPU integration or storage integration. So not use the CPU, but directly stored to the GPU. More different data tiers, like using different NVMEs or different storage patterns, and also supporting multiple clusters across federated environments. And also improving the API for machine learning engineers on a Jupyter notebook, the Python SDK. So lots of different enhancements coming up. So it is open source. We say it's ready for production, but we recommend like testing it out and also join the community calls, look at the GitHub issue, welcome any contributions. You can clone the repo, deploy with Helm. Yeah, so improve your machine learning training. So that's it. I don't have any more slides. Thank you so much. So with that, I'll open it up for some quiet Q&A. If you.
So I have a question regarding if I enjoy the training. How is the data being fetched? It's fetched randomly from each one of the data caches, or there are multiple strategies that I can, for example, use if I have the options?
Yeah, so depending on how much you need, so that you can set it up as a loop, right? So like, I mean, I can show you a little bit more of the script, but yeah, we don't have per se like a specific strategy. It's more about how you need that data for your training. But you can set up a loop to pick up that data from the different workers. But also, if you could have data locality depending on if you're doing distributed training. And in this case, I'm doing something very simple, right? So it's just like a kind example. But if you're doing distributed training, maybe you will have your worker node 1, and you have some training happening on node 1, and then you have some training happening on node 2. So you would actually need to write in your Python code, pick up for this specific data that you're going to be using in node 1, pick up all the data from that node, right? That's the recommended way, but I mean, if you have multiple training jobs too, then you have to figure out how to do it, right? So like,
It's something that you need to specify manually, I mean.
yeah. So we don't have like a, but that's a good question. Yeah. Yeah, that's something that we could probably improve upon, like some way to more efficiently, pick up the data depending on the different use cases. Yeah.
And in the transport layer, is there some kind of compression going on, or if the data cache is composed of X bytes, we're going to see X bytes on the network?
We are not doing anything with compression, but it's more about what Aeroflight provides, so in the back end, yeah. Okay. Yeah, so we're using, so this is built in Rust, and so it's using the Aeroflight library, right? So yeah. Yeah, question?
I have a related question to that. So I don't know Aeroflight well, but you mentioned that it does single copy, but this is only in between, not GPU memory, but only ROM memory, right? Or does it, and you mentioned also that there will be something for direct GPU memory.
Yeah, we don't have the GPU direct memory storage or copy yet, right? So we just rely like on Aeroflight, API again. Yeah. So and there will be some. There's no conversion. So I think with Aeroflight you don't have to serialize and deserialize the data. So it's more efficient, but I think it would make sense to have data locality in the node to make it faster, right? So, and using standard DRAM now, but not like GPU memory yet, yeah. But I mean, if you have a training a model, you will definitely use some GPU, like some form of GPU, right? Like you're training like some large model. Any other questions?
You
Yeah.
mentioned that reading Paki is actually faster. Do you have any numbers on if you read Paki files directly versus using the Arrow data
Well, yeah, I mean, if you're reading Parquet directly, Parquet is typically stored like in a blob storage. Yeah, so actually, like the demo I didn't show, but like I also had a fallback to just read the Parquet files directly. You could read that, but then we don't have the metrics yet because we haven't like measured it. But given the libraries and the mechanisms that we're using, we believe it's faster, right? So yeah, and then with Parquet files, you would have to just like go to S3 across the network, right? And there will be some delay there. Yeah, that's what I can think of. Any other questions? How much time do we have? We pass. Okay, cool. Yeah, if I mean, I can show you more demos. Like I have the fallback mechanisms if you're interested in how long it takes to just pick up the data from blob storage compared to just feel free to reach out to me. Yeah, there's some delay there with Apache Iceberg too, because you're looking up a table there. So, all right, thank you.